If you looked around here in this room, can you identify a gadget which works here but will also work in space?
That's a good question. I don't think any of the things here in this room can survive.
Let's say you are trying to monitor a particular point on Earth every 7 days or every 3 days. And when the monsoons come, you are not able to get the imagery and then you get frustrated.
When we started, we tried to use data from multiple satellites, but because of current existing satellites being separated over time, we could not solve the application. That's where what we do, something that's we are terming is SyncFused. We took information of a synthetic aperture radar image and an electro-optical image. These two are very complementary in nature, and together information they provide is a very complete information.
We are sandwiching camera and radar into one platform and making them synchronously acquire data from space.
That's where it started, right? That we need to put both of them together and we need to launch a satellite.
So Mission Drishti is the world's first satellite that will provide SyncFused data.
To have your own satellite, the amount of engineering that gets into it, it's amazing, right? You can test only so much on the ground, but once it is there in space, you can never get it back to repair it. So your engineering has to go right in the first shot.
There can be no tables that can be left unturned.
At this juncture, we found that we should be learning a little bit about space launches. Exactly at the right time, we got this opportunity by ISRO, where they have very interesting final stage of the rocket, which is called POEM.
3, 2, 1.
So POEM is your PSLV orbital experimental module. Now to enable quick prototyping, quick testing of anything that would go to space was the opportunity offered by InSpace. We were the last NG to get into POEM.
March is when we confirmed to ISRO that we will join this mission. We started designing. It took us two months to close the design.
During that phase, identifying that we've selected the wrong component, it's not gonna work for space. We need to take some extra measures. If there's a component as simple as let's say your IC, if it is not of a certain kind, if there's any adhesive used, if there's any air bubble inside, it's gonna blow in the space. So what measures can we take just to ensure that the mass is also not increasing a lot, but a same or the similar IC is getting used? That was a beautiful challenge to solve.
Towards the end of August, we got a date of that we have to deliver project by September mid. We were ready with our dummy model, and the first testing happened at the end of August, which is the vibration test.
When the rocket is being launched, as soon as the thrusters turn on, it's 2 to 3 minutes of extreme rigorous vibrations that the satellite and the payloads go through.
So September we did shock testing, then we stepped into the flight model. From September to October we are doing all the environmental tests.
Bigger challenge comes is of temperature. Based on where you're going on your orbit, your temperatures and how quickly they change can vary a lot.
We're facing a lot of issues, and the timeline was very, very strict. Like, we had to get the payload ready by 7 and catch a flight at 9. So that was when I thought, okay, you know what, we need to give it our all, because otherwise this is not happening.
Towards November, it's all the compliances which we had to do with ISRO, and then here we have fit the launch during December.
We have handed over the payload to ISRO, and it is now ready to launch. And when that happens, we will be waiting to collect our data.
The data will beam down from the platform to us. The software on the payload is completely autonomous, so it will perform all of its activities as soon as it is triggered. So 9 months or around less than that is when we are actually going to space. So that's a very quick turnaround for a space object.
One work which is left is that we have to plan to go to visit the launch.